right, we are live. Welcome. Thank you all so much for joining us for today's virtual event, Decoding Stress, how eye tracking and EEG reveal insights into air traffic controller workload. My name is Asha McManus, and I'm the Senior Director of Global Marketing at SmartEye. I just wanted to give some brief context as people are arriving, and we are going to talk more in depth about this. But today we are featuring a customer who will share some of his groundbreaking research on the topic of understanding the stress response of air traffic controllers using eye tracking tech from SmartEye. So we'll cover today how these insights can help improve airline safety, optimize performance, and really shape the future of air traffic management using biometric data in high pressure environments. So with that being said, I am thrilled to host both of our expert speakers today. We have our own Ulf Lofberg, VP of Research Instruments at SmartEye, and we have Lothar Meyer, Safety Engineer at LFV. Ulf and Lothar, did you want to briefly introduce yourselves before we dive in? Maybe we can start with our guests, Lothar.
Yeah, Lothar Meyer, my name. I'm a researcher in the role of Safety Engineer at LFV, a navigation service provider in Sweden. And my specialization is not only safety, it's human factors in combination, using empiric means to give safety evidence for new procedures, new techniques. And eye tracking is one of my specialized domains. Yeah, since many years. And that's pretty me.
Awesome. Welcome. And Ulf?
Hi, everyone. A warm welcome from me as well. My name is Ulf Lofberg. I'm heading our Research Instruments business unit at SmartEye. Been doing sales and business development for some time, and recently I switched over to Research Instruments VP. So I'm very much looking forward to this today, and thank you.
Awesome. Well, it's so wonderful to have you both join us today. I am going to hand it off to Ulf, over to you, and I want to pop back in at the end to field you guys some questions. So good luck.
Thanks, Ashley. So SmartEye was founded in 1999 and has grown into a sizable AI powerhouse specializing in tracking human behavior. We're now more than 300 employees spread across multiple continents. Our headquarters in Gothenburg is in Gothenburg in Sweden. And by now we have multiple offices in Europe, US, North Africa, and Asia Pacific. The SmartEye stock is traded on the Nasdaq First North since 2016 in Stockholm. Starting 1999, we have developed unique software and hardware products that allow tracking of human behavior. Initially, we supplied the research market, especially automotive, but also aviation, with head and eye tracking devices. Since then, the technology offers added ability to track also upper body movement, facial expression, and emotion, as well as decoding of dangerous behavior while operating mission-critical systems. Hence, SmartEye today also delivers into additional verticals and also commercial use cases, not just research. 3 years ago, SmartEye acquired 2 companies that would bring added technical capabilities. Especially the automotive production product offering was strengthened by the addition of Affectiva and iMotions, supplementing capabilities like Emotion AI and real-time multimodal biometric sensor fusion analysis. Today, SmartEye is divided into 5 units. On the left, you see automotive solutions and applied AI systems. These units supply driver monitoring systems and interior sensing solutions to the automotive commercial use case for major car production projects and for aftermarket. Automotive Solutions has so far won 359 design wins with 22 global automotive OEMs. More than 1 million cars are already on the road today with the SmartEye DMS solution. In the middle, you see business unit Research Instruments. This unit has been developing the SmartEye Pro head and eye tracker for more than 2 decades. SmartEye Pro is an advanced and unique tracker that offers unparalleled performance both regarding operational robustness and data accuracy, and it also boasts the broadest field of view on the market. The tracker can be installed anywhere and function in any environment. The system is complete and standalone and consists of hardware and software, and ultimately delivers raw data in real time. It's predominantly used for research even today. but it also formed the basis for the development of the solutions integrated into the automotive commercial use case, as well as when we recently developed a customized solution for daily use of eye trackers in the verticals, assistive technology, and pilot training. Hence, I like to think of research instruments as the original unit and the cradle of development of eye tracking into new verticals. The acquisition of Affectiva and iMotions did not only expand our technical capabilities within automotive production, the two companies also complemented our product offering in the research field. The Boston-based company Affectiva now forms the media analytics unit within SmartEye. The product name Affectiva remains, and the product itself has expanded its tracking ability since now also eye tracking is included. So on top of decoding emotions, Affectiva now also gives insights into subjects' visual attention. Affectiva is a remote camera-based analyzer of facial expression that reports on feelings that we express in our face. The product is used by 90% of the world's largest advertisers and 26% of the Fortune Global 500. The Danish company iMotions is a unit within SmartEye, but remains its own entity. The iMotions premium software platform is a multimodal data gathering and synchronization tool that allow biometric sensor data to be analyzed and visualized jointly and simultaneously. Of course, both SmartEye's and Affectiva's products are integrated, so the head and eye tracking data as well as emotion AI data can be added as input into studies managed by the iMotions platform. iMotions is used by more than 1,300 research organizations around the world. So if we focus on the research side of our business, here you can see a list of industry verticals which we work with. So all the mentioned research products, iMotions, Affectiva, and SmartEye Pro, provide researchers with insights in aerospace, assistive technology, aviation, automotive, clinical research, communications, medicine, neuroscience, psychology, and user experience research. Here are some examples of our customer base within the research field. You find some of the most prestigious names in the industry, and you can recognize our spread among commercial customers, private and governmental institutes, as well as universities. I want to mention the concept of multimodality briefly. So combining the original SmartEye head and eye tracker, several other biometric sensors, and Affectiva's emotion AI under the umbrella of the iMotion software platform comprises a complete product portfolio used in many research studies to investigate individual measurement points, but targeting a holistic understanding of human behavior. And eye tracking is a fundamental part of understanding and predicting human behavior. So what is the in-house SmartEye portfolio in terms of eye tracking? So the basic system offering contains two sets of hardware. So SmartEye Pro, DX cameras and flash hardware, high performance, small form factor, multi-camera solution catering for up to 8 cameras and allowing a field of view which is broader than 180 degrees. We also can model vertical as well as horizontal field of view. The SmartEye XO bar tracker hardware. This is as well high-performing equipment, but it's a fixed hardware configuration. So it is, in a way, a two-camera, two-flash configuration of the SmartEye Pro system. But putting it into a package like this makes the use a little bit easier, more sort of plug and play. The standard SmartEye Pro offering includes calibration-free gaze, precise gaze, and a fused combination of both gaze algorithms, a unique 3D world model which enables reporting of gaze intersection with predefined objects without post-processing. Saves a lot of time. And last but not least, all data output is available in real time over a network. The SmartEye Pro software features optional modules. So we have data delivery to vehicle CAN bus, facial feature positions and movements, so lip movement, nose, ears position, eyelid movements, and eye corner, nostrils positions, etc. We have an activity model which today includes detection of speaking based on lip movements. There is more to come there shortly. We can do infant tracking as well, drowsiness reporting, and of course the Affectiva emotion AI integration is here included as well. Difference is you don't have to add additional camera for the Affectiva module. You can use the eye tracking cameras. And finally, GPS module, that's a piece of hardware if you track in a moving vehicle, for example. And then there's some additional hardware that can be deployed for practical reasons as well to make the installation or the study easier. So what does it look like? This is an example of installation of SmartEye Pro in a full flight simulator for studies in aviation. You can see we have multiple cameras and multiple flashes. This installation caters for tracking of both pilot flying and pilot monitoring. So we have two systems, one for each pilot. The small form factor here is critical. There's not a lot of space in a cockpit, so you need to have something small so that it fits, but also small enough not to be too visible. So our small form factor has a very important function here. The freedom of placement regarding camera and IR flashes, there's a flexibility and a scalability of the system, which allows us to basically track in any application in any environment. So here are examples of full flight sims, UAV workstation, air traffic control scenarios, but also tracking in difficult and moving environments. So the simulator to the right is actually a spinning and turning simulator, which creates a lot of G, a lot of movement and shocks, which usually can create a problem for multi-camera systems. But it works. This is a system currently online. It's called the Kraken. The simulator is called the Kraken in the US. The single unit cameras in a multi-camera system, they have each their own lens, which means we can position the cameras on different distances. We can play with what we call the head box. So you want to be able to move freely. One of the tricky things with a remote camera system is that you can't walk around. But as long as you sit, you're still able to move a lot. And we can adjust this head box so that you can move and behave as you usually do in these environments. The expanded field of view means basically you can turn your head to the left and right and tracking is still maintained, while we maintain also a superior accuracy. So a broad field of view with a high accuracy within this whole field of view. And as you can see on the lower video here, if we can replay it, thank you. When we turn off the light, tracking still works. That is because we have our own IR illuminators. So if we summarize what we're doing with research in aviation, we're basically in two environments when it comes to aviation. One is in the cockpit, in simulators, which is the usual case, but some of our customers are also flying with the multi-camera system. That's kind of impressive, I think. Usually in the cockpit, it's about HMI design, pilot training, or pilot state monitoring. What Lothar will tell us much more about today is the situation in an air traffic control operator scenario. Here it is about training, which Lothar will tell us more about. It can also be about operator monitoring in terms of workload. I think in some situations we've also done, monotony-based research, and so their drowsiness also comes into play. So that's what we usually do in the air traffic control scenario. But let's hear it from the real professional, so to say, instead. I'm very happy and excited to hand over to Lothar Meyer from Luftfahrtverket. Thank you.
Thank you so much, Ulf. Yeah, the topic for today is workload prediction using eye tracking technology. And this is a specialized work environment for air traffic controllers, which is called en route control. And I've prepared some basics for you so that you understand what's actually the magic about workload. So hard on Staveland defined workload as a hypothetical construct that represents the cost incurred by a human operator to achieve a particular level of performance, which actually means it costs something, cognitive resources, to perform. On the right side, you have the very original document where the concept was first taken up by Jerks and Dodson, 1908, and they actually put mice in a black-white discrimination task. They had to recognize if this is black or white in a maze, and they were stimulated by electrical shocks. So 1908, that was the ethics is not a point of discussion, but you see that on the on the diagram, there's an inverted U-shape, which says that the specific stimuli, you have the least rate of errors. Yeah, and that was where everything came from over the decades, over 50 years of theoreticalization. It became the today inverted workload curve that you see in the middle. So the optimal workload in the middle, and then you have unknown overload on the left and right side. So it's pretty much a small frame in the middle. That is the best for the air traffic controller. How do we manage workload in ACC today? You see a photo in tower control right now, and there are so many instruments, so many information sources, tasks that need to be performed at a time to keep track of all aircrafts that are on the aerodrome platform. And air traffic controllers have actually a set of balancing their workload today, because otherwise, if they have too much workload, then that might risk that they oversee something else, staying in target fixation effect or something else. So it's beneficial to actually have one day a workload monitoring tool that helps the EDCO to actually keep track of the workload, or even train a good self-estimation. The self-estimation of the EDCO, the air traffic controller today, is based mostly on self-assessment. So it's just feeling in the fingers. So how much is it? And the paradoxon is this relies so much on self-awareness and the capacity to do that actually when I need it, we are bad. The human is bad in self-estimation of workload in the case it's really needed. The same applies to fatigue, where we have the human in general has considerable drawbacks in doing that qualitatively. So there's a requirement for non-intrusive measurement of workload to support this, and the best choice was eye tracking, because it doesn't touch the EDCO so much. So the less there's contact to the EDCO, the better it is. So how is it done today? There is something that EDCOs have today, which is called the Center Flow Management Unit, CFMU, which predicts the forthcoming air traffic as a blue line. You see it here over the next hours. And then you see a yellow line. The yellow line is actually a threshold, which the EDCO is allowed to stick through a while, but just temporarily, like a peak. And then the blue curve should be under the yellow line again. But if it's too much workload, what the EDCO perceives or self-assess, then the sectors must be split in two. And then an assistant comes and takes over a part of the sector. If the orange line is reached at the very far upper side, then it must be splitted instantly. So that is how a workload is managed today. There are more stories I could tell, but I take that later, perhaps. So we did an experiment testing eye tracking for workload measurement, and therefore we performed a series of experimental runs or simulations. In the Top Sky simulator, here you see the experimental setup with an EDCO, looking at the primary instrument, which is the radar screen. And you see a traffic situation on the radar screen, which shows several movements in the airspace. And the task is to detect conflicts, to probe solutions, implement the solution like clearance, lateral clearances, to avoid the conflict and to keep all movements well separated from each other. So it sounds easy task, but I tried it myself. It's pretty hard. So it's a tough job to do this. On the right side, you have another secondary screen with flight plan information, which was not that relevant now for our study, but it belongs to his work environment. That's why we wanted to have. On the left side, procedural information on weather chart. As well, secondary information that just sometimes to make the EDCO feeling like at home, to keep all this information in the circle and not to save it away in the experiment. In the middle, under the primary screen, you see the eye tracking bar, the Smart IXO, which was tracking the eye. On the head, you see also, besides the headset of the EDCO, you see also an EEG, measuring the brain activity at certain points. And that gives us also a clue of the workload based on EEG measurement. Aside of that, we had also subjective measurements from Cooper-Harper scale. I will come to that at a later point. So you see here our traffic controller in a time-lapse video, and that was actually 40 minutes, and we pressed it together in, I think it's 25 minutes. So we start all over again here, and you see that the movements are in the airspace sector, they move through the sector, and the air traffic controller is very busy with giving clearances to keep them all well separated. That was the task. We come to our simulation study setup, and we had some requirements for that. The red field should have popped up later, but okay, I will bridge that. So we had the Smart Eye XO for the eye tracking part. Then we had the Brain Science EEG with the measurement of workload, vigilance, and stress level, which are called neurometrics from the House of Brain Science. So you're very welcome to have a look on your own where that comes from, but we cited it in our papers. And we tested 18 licensed EDCOs in their Top Sky simulator, which is the original simulator from them. So they use it for their own training and education. We had 3 runs per EDCO, a light run, a medium run, and a high workload run. So each one 40 minutes, which results in 54 simulation runs in total with 3 different work conditions or scenario conditions. Yeah, we had the workload safe assessment, and we had the eye tracking and the EEG as the 3 primary means of measurement. You see in the middle a box with the requirements of the eye tracking. That was how we started our search for an eye tracking manufacturer that suits all these points. And after several tests and discussions, we end up with Smart Eye XO is the best choice. And that was because it's so easy calibratable. And the EDCOs liked it instantly. That was our conclusion from that time. And the 200 Hz guarantees us that we have even the smallest fatigue effects and workload responses from the eye movements in the data set, so that we can see that in the analysis. Even so, eye blinks can be very quick and saccades, revealing even the smallest details of fatigue effects. But fatigue is another topic. It's now about workload. Yeah, next slide, please. So we used the Cooper-Harper scale, a scale from 1 to 10. And most of the time, the workload was between 4 and 6. Like there's a bit workload, but not too much. And this is a subjective scale, so the EDCO assessed him or herself. We follow a multivariate approach that we combine these 3 measurements to actually keep them consistent and see how do they correspond to each other or correlate even, and to predict the workload from physiological and subjective measurements to behavior-based, which is our eye tracking. Yeah, so these 3 must be kept consistent, and then it's a sign for high validity. Yeah, after we collected our data, we used 15 eye tracking and head movement variables and transformed them to so-called statistical summary features, which is done by mean, standard deviation, median, minimum, maximum, total number, and duration. So, so each variable is transformed to several features. And then we have the label, which is the Cooper-Harper and the EEG, which is allocated to each point of the measurement. So we know at this point of the eye tracking, we had this workload level from EEG or the Cooper-Harper. The Cooper-Harper, we split it into 3 classes, which is 1 for low, 2, 3 for medium, and everything higher than 4 was considered as high, so that we have a fair distribution of the samples collected. So we try to set the borders also that we have some variance in the data as well. And the EEG, we split it into percentiles, so that we have also here a correct set of variation in the data. My PhD student, Anastasia Lemetti, was assigned with the task to do the machine learning itself. And here you see the models that we used There were 5 different models she applied, and machine learning techniques, which this is actually not inside my competence envelope. So if you have any questions, please ask her directly. I'm not an expert at this, but at the end, it's important that we have 2 quality metrics for evaluation. That's the accuracy, which is the proportion of all correct predictions, and the macro F1 score. And the F1 score is nearly the same as the accuracy, but it is more for imbalanced data. So if we don't have in the bin a 50-50 share of white and black balls, then it's imbalanced data, and that's better to take the F1 score. But we didn't find any contradictive results. So accuracy did nearly say everything everywhere the same as F1 score. And now you see some of the accuracy results right now. So if we use 58 features for predicting Cooper, Harper, and EEG, and in the comparison of all 5 models, then you see that we have some that have quite a good prediction performance. And this is the HBBC with 84 to 85%. And if you take the lower 2, it's even 96%, which is marked in the bold. So what's the difference here? The upper 2 are actually the 3 class, and the lower 2 is only a 2 class prediction. So meaning workload is low or high. That's the difference. And of course, if you have not so many classes to distinguish, then prediction accuracy becomes higher, of course. The more accurate you need it, the more classes you need to predict, the lower the accuracy gets. But 96 is quite a good result, we thought. So we reduced the features. That's an important step. Why do we do that? Every one of you that did already machine learning or regression analysis came to the point that you overfitted your model. And in the worst case, that can mean that you even decrease your accuracy by that. And this to avoid, the number of features need to be decreased in the best hope to get an optimum point, to find the point where you get the maximum out of it. So, and the problems that we avoid with this is overfitting, as I just mentioned it, but it's also about computational complexity and multicollinearity, that we have many variables that actually say the same, that are interrelated, and yeah, you don't want to have them at the end. It shall be a stable set of parameters or features that that are the most decisive. Yeah, and this is called the Hughes phenomenon, by Hughes, 1968, discovered, and make it so easy as possible. That's the importance here. Next slide, please. We look at the results of the reduction and feature selection. So you see that on one axis is the number of features. On the other side, on the left diagram, you have the accuracy. On the right side, you have the F1 score. And if you look at the shape of this, of the number of features and how it was reduced from right to left, then you see that quite a large area, the reduction doesn't do so much. It's only noise, but in total, the same level is kept and maintained. At a certain knee point, it becomes very sensitive to the number of features, and the accuracy, or the F1 core score, drops. So, and that was quite characteristic for F1 score and accuracy, that we have this knee point where a saturation area is distinguished from a high sensitive area. And that was very nice to see. We determined the knee point by a special algorithm with drawing these lines. We found that out. Yeah, so and we determined the knee point as the best point of economy. We said it's the best balance between model performance and the number of informative features used. It's a bit from aviation, best economy and best performance. So everyone that knows a bit about cockpit knows about these terms. So we come from aviation, we stick to aviation. So this is an overview of the analysis using the reduction. And the best economy, if you reduce it to the best economy point, you see that accuracy and F1 score more or less stay the same. They end up with 9 features and about 82 to 87 accuracy. And the same for the binary discrimination class or task. It's 94% for the accuracy and 78 to 82 F1 score. Yeah, so it's quite a huge reduction from 58, 9 to down to 9 or 13. And for the EEG 2 class prediction, it's only 6 features left. And that tells us quite much that actually you have much air in the bags that you can just press out without impacting the results so much. That was quite nice to see, I thought. For the best performance was a bit different. It was actually located in the high noise area of this saturation area where you have much noise. And we found it quite random where you end up. So it might be that the points only distinguish in some 1% point or less. And depending on some variations of the task conditions or the state of the EDCO that day, I think it will vary a bit in this noise area. And then the point is not so significant anymore. So we thought we would stick to the best economy in the future. So this is the same results from the table before, just visualized in areas. So you have these areas of best economy and best performance, where we end up with our prediction results and our models after reduction in the best economy and best performance also. And the full number of features is on the far right side. So what is the blue curve? The blue curve is actually expressing the trade-off between number of features and the accuracy of your prediction results. And you have to make a trade-off. Whether you want many features, and then you end up after the best economy in the saturation area. So then if you're up there, then it doesn't matter so much how many you choose. So in the best case, you have the best economy. But of course, the shape of the blue curve will a bit change depending on how many classes you want to predict and how much resolution do you want to have. So there might be some changes in the quality of the shape. And we call that the specific limitation of prediction. So along this curve, you can move. So we come to our conclusion already. We found some accuracy results for our prediction and some F1 score. So we lie between 73% for F1 score in the 3-class prediction, and for binary we have F1 score 87, which we think is quite good. If we think we just used eye tracking for predicting EEG and Cooper-Harper. So we found that quite impressive. And EEG, we were between 77 and 84, depending on 3-class or binary prediction. Yeah, so we found that we can make quite much with the with eye tracking only. So that was surprisingly high where we ended up. But we think also that this cannot be the only thing that we draw our conclusions from. So if we combine it, for example, with ECG or another form of stress measurement, it can be added on top. So I think that's the way to go in the future. That you have to combine it with other measurements. Eye tracking perhaps only is limited to what you have. So it's pretty much 87% for binary. Yeah, and we could reduce the number of features just with a minor loss of prediction accuracy. And we also found out head movements was not so much of relevance. The head movements didn't tell so much. The head movements has also the problems that it's very high task dependent. So meaning if we are sitting in a tower, you have many head movements depending on your workload, but that's all gone with en route where the head is only forward directed. So that was also a big difference to our pre-study where we sat in the tower and saw every time things are going on, then the head moves around, right, left, and up, down. In the future, we want to look more in the task, the subject dependency. So can we just take 20 EDCOs and then we have all EDCOs included, or do we need to recalibrate the machine learning to also catch up with other EDCOs that come in addition? So that's a bit the question now. How stable are we over the entire population? We will look into that in the future. We have 2 publications from DASC and EAP that were just presented September and October, and they are not in the public accessible database right now. But you can already take a screenshot from this and just wait in November. It's time to get a good publication on that. I'm just a project leader. You see that many of our colleagues are involved, which all helped to get these good results. And I'm just the point of contact. So email me in case of any questions. Machine learning directly to Anastasia, as you understood. And yes, thank you for your attention.
All right, I'm back. Great presentation, super fascinating. Last chance to send in a question if you have it now. One that came in that I think this is probably for both of you guys, but maybe we can start with it. I'm currently working on a stress management program for my company. How exactly will eye tracking tech be used in real time to improve safety in ATM? Will there be notifications sent to the controller in charge to go and rest? Will there be a supervisor monitoring the bio data and intervening in case the EEG and eye tracking parameters go off some limits? Would love to be able to put this check and recommendation. Do you guys have any thoughts on that?
Yeah, there's a kind of varying degree of escalation, how much you want to intervene. So I would say in the lightest case, you can have just a good training that operators become more self-aware about workload. So that it's a skill, like any skill in our lives, that must be learned and trained. And with such a workload monitoring tool, you can just say, okay, we make some exercises. And then you learn that by your own. That's the easiest case. You can make that with just some exercises and then say, yeah, that's your feeling if you're here up playing a game or yeah. And then you can go to the next phase that you have an alert system, which is quite intervening. And intervening is always the less good option because then people get complacent and say, well, the machine told me, so I have to follow that. In my eyes, not the best option to give alerts, which also perceived as a control system, which monitors you in real time, is oftentimes not accepted. And in also in a high class level, I would say it can be used for selection, for finding operators that have from nature a good feeling for their workload. How good am I with doing that? Or am I the cowboy that doesn't care at workload at all? Yeah. So there are different levels of escalation. Depending on your culture and your organization, you can choose the light or the heavy one.
Maybe just a brief comment from my side. We provide measurements, we provide detection. So we're not used to actually thinking creatively around how to react on specific detection or measurements, right? So I can only relate to the automotive industry, where cars today tell you that you're tired, or the car tells you you're not paying attention. And I know that there are extensive discussions now on what is the right reaction from the car. I mean, just to give a notification saying you are tired, for example, can be perceived as intrusive in a way. Although it's a safety measure, what do you do with the information? It's a very interesting topic, and I think different industries might go different ways.
Great points. Okay, next question about the eye movement parameters. So this might be a little more technical. Did you look into which of those worked the best or were related to workload predictions the strongest? So for example, blinks or horizontal movements or something else?
Yeah, surprisingly, the lists that we got after reduction and selection of features were not that stable as we thought. So there's not the one and only set that you use and that's it. The machine learning has generally the problem that it does not explain very much why it does do things, why do things. But there was one candidate that I found in all the lists over and over again. So after reduction, we get the lists out. So that was what was remaining. And then there was one hot candidate, and that was actually pupil dilation. So that was the quite persistent candidate. And we first thought at the beginning of our study, this is not a good candidate because pupil dilation is prone to illumination effects. So that is disturbing our measurements. But at the end, the reduction process said, no, this is the best prediction feature. So that's the only thing that I can say right now. But there will be a journal publication on that where we will extend the research that we have right now with these kind of results.
So this question is for Ulf. It's kind of a double up from earlier. So can you explain some of the unique challenges in implementing eye tracking solutions in environments like air traffic control, and how Smart Eye addresses these? And what advice would you have to organizations that are considering integrating eye tracking into their human performance monitoring practices?
Today we're talking about using eye tracking for the purpose of doing research studies that Lothar and his team did. If you implement eye tracking to use as a tool on a daily basis, so it is a integrated solution into the air traffic control operational station, then you would have to address multiple questions. Hardware integration, installation, where does it fit? And then the topic we touched before, what does it actually do? How does a measurement react on the data and then the processing of the data? In our experience, we've walked the path a couple of times now, once in the automotive industry, once in the assistive technology side, and also pilot training. Each industry has to find the way that it suits them. We're always ready to help out. We start with a test installation. We see what works, what does not work, and we adjust accordingly and move forward. And at the end, there is a solution which will fit everyone.
Awesome. And this is for Lothar. What are some of the next steps or the future phases planned for this research? Are there any new methodologies or technologies that you're considering for future studies, if you can comment on?
Yeah, for first, that's also what we applied for at the Swedish Transport Ministry. That is to mature this technology, that we really can use it for education purpose. And now it's more about revealing about the uncertainties of such a workload monitoring. That's the absolutely next step, because there will get questions like, oh, is this prediction accuracy always like that? Or does it also vary here and there, getting worse? I bet there's no problem, but do we have it also sometimes worse? So what does it depend on which factors? So we have to go through all factors and check each one after the other. Okay, what does it do with our prediction accuracy? So that is the uncertainty management for coming one step closer to an implementation scenario one day. And explorative, I would say the stream goes towards scanning pattern-based workload detection. So our scanning patterns from our eyes are much more prone to workload issues. So how I scan my environment, which information I use, in which sequence I do that, with a dwell time allocated, I will instantly see fatigue and workload effects in that, compared to a baseline where I didn't have that. So I think that will be the next step on an explorative level.
So that is all we have time for. I know we went a little over, but I want to thank our presenters, Ulf and Lothar, once again for making the time to speak with us today. Hopefully this gave some clarity on some of the exciting work happening in the aviation space with eye tracking tech that Smart Eye provides. And don't forget to sign up for our newsletter, follow us on social media so you don't miss out on our next virtual event. And thank you so much, everyone, and have a great rest of your day wherever you are in the world.